So this is chapter 7, and what we're going to start with is talking about the normal curve. So we're going to look at a couple different distributions here. So one is just going to be normal curve in chapter 7, and then there's something close to the normal curve that's slightly different we're going to look at as well. So this is going to be for a continuous random variable, which is mostly the emphasis of chapter 7, is what we do when we have a continuous random variable. So if you consider that vehicle emissions data that we've used several times throughout the class, we got this histogram like we have here that's really kind of bumpy. It's really kind of discrete. So you can visualize, we can visualize these data with relative frequency histograms, which we see here. Class intervals are chosen so that the rectangular represents a reasonably large number of vehicles. So we extended this is the emissions here. So we set our emissions class to 1 parts per billion. I can't remember exactly what it was. But we have a lot of cars that sit in this range. We got a lot of cars in this range, and we have this sort of wide class width. Vehicle emissions is a continuous random variable. So what we mean by that is like we don't have emissions of just 1 part per billion or 2 parts per billion or 3 parts per billion. We have things like 0.92 parts per billion or 1.15 parts per billion. Or is it million? I'm trying to remember now. Anyways, but we have something that's continuous. So recall that a continuous variable is one whose possible values that can be any value in some interval. So we can use any kind of class width is really what we're getting at here. So if we made our class width smaller, and we saw this when we were talking about histograms, I can change my class width, and it will make a little bit of change to look at my histogram. But what we see is that as my class width is getting smaller, this histogram is starting to look smoother, much smoother than this one is looking. So suppose that the sample of vehicles was very, very large. We can have like a million different cars in there, or billions of different cars. Because the amount of emissions is a continuous variable, there would be a reasonably large number of vehicles for each rectangle, even for very small class intervals. So I can make my class sizes very, very small, and I should have a significant amount of vehicles in it. So but basically I'm saying is I won't have data with a bunch of gap. I get something that smooths out like this. So what this gets us at is that if I have a continuous random variable and I had a huge population, I can just really start modeling it what we call a probability density curve. So like I said, such histograms with smaller class sizes are going to look smooth and can be approximated by a very smooth curve. And we've been doing this all along. We've been talking about kinds of different distributions, and we've been drawing these curves around them to kind of simulate what the shape is. And every time we do that, we're essentially doing a probability density curve. So the curve used to describe the distribution of this variable is called your probability density curve. The probability density curve tells us what proportion of the data falls within a given interval. So there is a formula for that curve. And if you knew the formula and you know a little bit of calculus, so calculus can help you estimate like areas under curves. So with the formula, a little bit of calculus, that's how we can figure out what proportion of data falls within given intervals. Like I said, there's formulas for these curves, and we're going to look at a very particular curve that has a formula for it. So the area under probability density curve between two values A and B represents the proportion of a population whose values are between A and B. So in this case, A is 3, B is 4. So if I know the formula for this particular curve here, like I said, there is some calculus that I could do, and I could actually tell you what this area is. And in this case, if I had done it, I'd find out that the area between 3 and 4 for this particular curve is 0.17. So that is the area, because Cumulatively, the whole area under a curve, under a probability density curve, is always going to be 1. And the reason that's 1 is because of the probability density curve. This is all my probabilities. It's really representing 100% of everything that can happen. So what this area is telling me is that if I change that to a percent, there's a 17% chance a random variable is going to fall somewhere between A and B. Like I said, there's a bunch of stuff they're kind of missing over here. Like, how do I know that area? That requires something that's out of the side of the range of this class. But if I could find that area because will tell me a probability. This is where we're going to start really talking about areas and probabilities. And just remember that they are representing the same thing. So once again, the properties of a probability density curve. So the one I already told you is that the area under the entire curve should equal 1. Because like I said, the probability curve, it represents everything. So it's going to be 1, which also means 100%. The region above a single point has no width. So if I look at just A by itself, it has no width and therefore it has no area. So when we talk about the areas or we talk about probabilities, we're talking about probabilities over an interval instead of a particular value. So if X is a continuous random variable, the probability of a single value is just going to be A. So we're going to find probabilities of intervals. So we find probabilities of intervals, not single values. And also because if I look at a particular point, like just at A, if A was 3, like what's the probability of 3? It's just going to tell me 0 because I have no width to this area. So that means that when I'm talking about probabilities, that this probability that a value is between 2, like A and B, so this is B out here. So the probability of this shaded region, or the shaded region is the probability of something being between A and B. That also is the same as the probability of it being between A and B and can be A or B, so inclusive. So those have the same probability. So we're kind of interchangeably when we talk about these intervals, sometimes we're going to have everything's a less than, sometimes it's going to be less than or equal to. So for example, we're going to consider the probability density curve with some areas indicated. So somebody went through and figured out the areas for this particular curve. What we see here is that a proportion of the population is going to be between 0 and 1. So let me mark that again because I see that maybe a little small on your screen. So that's my numbers there. The proportion of the population that would be between 0 and 1, we see would be that 0.3, or 63% of my population is between 0 and 1. Whatever that means right now, we don't know. We just know the proportions. The proportion that of the probability that a randomly selected variable is between 1 and 2 is the same thing as saying the proportion between 1 and 2. So it means the same thing. And as we see here between 1 and 2, that area is going to be 0.23 or 23%. So if I want the proportion of the population that's between 0 and 2, well, that's just 0.63 plus 0.23. We just add those together to get the area from 0 to 2. So we get 0.86 or 86%. The probability of a randomly selected variable is greater than 2. So we're talking about this area right here. We know that this whole curve represents 1. We know it's all represented as 1. We know that anything less than 2, so right here, this is the probability that x is between 0 and 2. This is the probability that x is between 1 and 2. And this is the probability that x is between 0 and 1. So if I want this here, the probability that x is just happens to be greater than 2, well, all that means is I need to take 1 and just get rid of the probability that it runs between 0 and 2. We get that 0.14. So it's a 14% chance that we have a value greater than 2. There's many different shapes we can get to our distributions. Like here, we had this, only it was skewed to the right. This is a uniform distribution. So there's some information that we do know about certain distributions. So we don't actually, I would have to do a bunch of work and find a formula for a curve and everything. So a uniform distribution is one in which all regions are equally likely. So that means all my events have the same probability, essentially. Singular events have the same probability. The probability curve for a uniform distribution is a horizontal line. So imagine that when a traffic light turns red, it stays red for 30 seconds before turning green. If you pull up to the light when it is red, the amount of time that you will wait before the light turns green is uniformly distributed between 0 and 30. Okay, so that means that whenever I pull up, if I pull up here, if I pull up here, the amount of time you wait for the light to turn green, that probability that you would have to wait is going to be the same. So it's really that probability that we're talking about, not the wait time. So if I wanted to figure out what's the probability that I would wait, say 10 to 15 seconds after the flight, we're talking about this area right here. So all we're looking for is just an area. So remember, this is all supposed to represent 1. And because you're waiting 30 seconds, that means that the height of this distribution would actually be 1 over 3. Or 1 over 30, sorry. So we have 1 over 30 for the height. The width from here to here is 5. So we get 5 over 30, or 1/6. So there is a 16.7% chance that I'd end up waiting somewhere between 10 and 15 minutes for this light to turn. That's how we kind of use a uniform distribution. Like I said, we know these areas represent probabilities. Was the probability that I would wait less than 10 seconds? Well, that is just this area right here. So once again, that area is a 30, but the width would be 10. So that would be 1/3, or a 33.3% chance that when I pull up to a red light, that I am going to wait roughly 10 minutes. So like I said, so it's uniform. Whenever we pull up, it's just the same probability if for each individual time frame, assuming we could calculate that. So you get this uniform distribution. We're just trying to find those areas. Another example. Okay, wait, sorry. We just did this one. Okay, no, we didn't because I did 10 to 15. So this is 5 to 15. We want to figure out what the probability of the wait time is if we had to wait between 5 and 15 seconds. We're looking for the probability that I would wait. My X value, my random variable, is between 5 and 15. And as a reminder, this probability is the same as this probability. So if I even put inequality in there, that equals the same. So this area here has a height of 1 over 30 and it has a width from 5 to 15, a width of 10. So 130 times 10, we already saw this earlier. That's going to be 1 over 3 or 33.3% again. All right. So if we had to construct this on our own, the wait time for a bus for the wait time at a bus stop for the next bus to arrive is uniformly distributed between 0 and 10 minutes. So whenever I show up, my probability of waiting 1 minute or 2 minutes or 3 minutes is uniform. So, well, let me make my distribution again, make it a little nicer looking. Like with an actual straight line. We'll put it down here. There's my distribution. And I could be waiting anywhere from 0 to 10. 3, 4, 5, 6, 7, 8, 9. Okay. That means if I make this distribution, put a little box here for it. It's going to be uniform. Like we said, it's going to look like this. This wait time is going to have the same probability no matter what. And what we would say is the height is because this is over the course of 10 minutes. The height is going to be 1 over 10. Like when it was 30 minutes, it was 1 over, or 30 seconds, it was 1 over 30. Because once again, we want to make sure this area equals 1. So this length is 10, but this is 1/10 of that whole area is going to be equal to 1 because that's my probability distributions. We want to figure out what is the probability that my wait time is less than 3 minutes. So we're looking at from here to here, less than 3 minutes. Sorry, something popped up on my screen. There we go. Oops, sorry, I went 2 minutes out. Let me go 3. 1, 2, 3. So we're talking about this area right here. So the height of that area is 1 over 10, but the width is 1, 2, 3. So my probability would be 3/10 or 30%. The probability of my wait time, so X, is going to actually be greater than 6 minutes. So we're looking at this area right here. And once again, the height of the area is 1/10, but the width is 1, 2, 3, 4. So that would be 4/10 or 2/5 or 40%. The probability I'm be waiting at the bus stop for more than 6 minutes, there's a 40% chance that will happen. The probability that the wait time is going to be between 3 and 8 minutes. Try and get rid of the little spot there. Okay. So do that in green. So we're looking between 1, 2, 3, and 4, 5, 6, 7, 8. 8 minutes. That's this area right here. So the probability that my random variable X, my wait time, is between 3 and 8. Once again, That area is going to have a height of 1/10 and a width of 1, 2, 3, 4, 5. So 5 over 10, or 1/2, or 50% chance. There's a 50% chance, and I'm waiting between 3 and 5 minutes.